My name's Yang Yo, and this talk will give you a brief introduction of our work, Canonical Voting towards robust oriented bounding box detection in 3D scenes. Oriented bounding box detection is a challenging problem in 3D scenes. Recent methods like VoteNet bring voting into detection by generating direct offsets towards object centers. These centers are then aggregated by some clustering algorithm to generate proposals. Refined offsets and orientation classification are then predicted with an additional head. However, we find that for many points, the predicted orientations and direct offsets are inaccurate, and the proposals may miss some occluded objects. To handle this problem, we disentangle direct offset towards object centers into three parts: local canonical coordinates, box scales, and box orientations. In LCC, all objects are consistently aligned and centered, lying within the unit bounding box. To understand why predicting LCCs can be better and easier than direct offsets, let's take an image as an example. Suppose we would like to output direct offsets or LCCs for each pixel with 2D convolution. In the left, we see that each local pattern is mapped to its corresponding direction. When the image rotates, different parts of the dark are mapped to the same output offset. This is how direct offset works, since it does not go with the orientation. It is hard to identify different offsets based on the divergent input patterns. In contrast, we can see how LCC works from the right figure. No matter how the image rotates, patterns that belong to the same part are always mapped to the same LCC in canonical space. This makes it easier to learn the relationship between inputs and outputs. The network only needs to classify different parts. Similar ideas on regressing local coordinates have also been explored by previous methods like Knox. However, it has to do instance segmentation first, and then computes the bounding box for the detected single object. For multiple instances, it fails, and some novel voting scheme must be introduced. Our proposed pipeline first uses sparse convolution backbone to predict the surrogate LCC scales and objectness. Then, a canonical voting scheme is proposed to generate proposals based on the vote count. In the canonical voting scheme, each point would enumerate possible orientations and generate votes on a circle. Ideally, when enough points get processed, we would end up with a vote map with peaks corresponding to those object centers. Notice that the orientation is recorded in each vote and then averaged over all the contributed points. Due to the object symmetry and the exhaustive search of orientations, there will be some false positive peaks in the final vote map. In order to eliminate them, we back-project the points with candidate bounding box to get the back-projected LCCs, and then compare them with the network-predicted LCCs. If they do not match, we reject them. This greatly increases the precision of our model. The whole pipeline is shown in graph. Experiments show that our method achieves state-of-the-art on three challenging benchmarks, namely ScanNet, SynNN, and SunRGBD. We also find that when trained separately for each class, our model can perform even better. Here we show the decoupled orientation and translation error of our model compared to previous methods. It can be seen that previous methods all have difficulty identifying the orientations, while our method could give much more accurate results. The running time of our method is also comparable thanks to the highly parallelized voting scheme. Thanks for listening. Code data and more results can be found on our project site.